tartaric acid. Tartaric acid exists in 4 forms. A D-tartaric acid, D-tartaric acid, then L-tartaric acid, then an equal mixture of D-L-tartaric acid and mesotartaric acid. Okay, and how would you distinguish between meso and DL? How to distinguish? How will you distinguish? Suppose you are given 2 samples and you have to find out whether, by experiment, whether these 2 samples are DL mixture or meso. Remember, DL mixture is having optical rotation 0. Meso is also having optical rotation 0. So you cannot compare those two. By comparing the optical activity, you cannot distinguish whether it is DL mixture or meso. Okay, if it is only D or L, you just have to find out the optical rotation and see if it is having an optical rotation, it is either D or L. But meso will not have an optical rotation. But if you are given a DL mixture which is equal amount of plus and minus isomers, optical rotation will be 0. Therefore, that cannot be used as a method of separation. But the name itself will tell you DL is a mixture. DL is a mixture. And you have studied from the basics of chemistry the difference between, but the meso is a compound. Meso is one compound. DL is a mixture of 2 compounds. Okay. And one compound cannot be separated further. Cannot be further separated. Cannot be further separated. Normal because it's one compound. But DL mixture can be separated into. They can be, mixtures can be separated. You have studied from basics of chemistry. Can be separated by some method. We will see later what are the methods of separation. Can be separated by some method. Into D and L isomers. So the one which can be separated into D and L, you call it as DL mixture, and the one which cannot be separated is known as the meso compound. So this is how you distinguish between meso compound and DL mixture. Now let us see. I told you racemic mixture. Racemic mixture is an equal mixture of D and L isomers. But there is a term called racemization. Racemization. That is converting one enantiomer into a racemic mixture. Remember, it is not a method of making racemic mixture. It is not a method of making racemic mixture. It is a method of converting either one enantiomer, either D or L, into a racemic mixture. There is a lot of application for this. Okay. Now we will take up an example. Let us take D-lactic acid. We will take D-lactic acid. D-lactic acid having the structure C double bond O, single bond OH, C OH and CH3. This is D-lactic acid. Okay. Now you can tautomerize this. This can be tautomerized. This will exist in equilibrium. See here. This is what is meant by tautomerization. You get COH, OH, double bond OH, and CH3. Okay. Now this can again come back. Okay. Remember, this is planar. This one is planar. So when this again, when it tautomerize in the keto form, it will form an equal mixture of both of these. Plus OH, H, and CH. Okay. Now you can induce this tautomerization process probably by adding some sodium hydroxide and under anhydrous condition or sodium methoxide, NaOH. You can then reach this anion. Okay. And once it forms it again, when you are adding the water into this, it will regain the proton and will form the racemic mixture. So this is one enantiomer. One enantiomer is converted into a mixture of equal mixture of both enantiomer. This process is known as racemization. Don't tell that it is a method of mixing equal amount of D and L. That is not called a racemization. Please don't write that answer. Many students write that. So don't do that. That is not racemization. Okay, let us look at next one. That is resolution. I told you a real mixture is a mixture. DL mixture can be separated, mixtures can be separated, and therefore DL mixture can be separated into D and L form. This method is called, or the methods used to do this are called, this process is called, this is called resolution. This is called resolution. Okay. So method of converting a DL mixture, separating the racemic mixture into D and L enantiomers, separating DL mixture into D and L enantiomers. This is known as resolution. Now there are different methods of resolution. We'll just explain one by one. The first method of resolution is mechanical separation. Mechanical separation. Now mechanical separation is what is the word mechanical separation means you are picking with your hand. Picking with your hand. Okay. I'll give a typical example. Suppose you have 50 pairs of chappals. 50 pairs of chappals. Okay. Then it is all mixed up. Suppose you are asked to separate the right and the left. Okay. You can keep 50 right and 50 left. Same is the case with gloves. You can separate them. You can separate the right-handed and the left-handed. This is by observing the material and identify the mirror image nature. Okay, so your left chappal will be a mirror image of the right one. So you can easily separate them. So in the case of compounds, in the case of these compounds, what you can do is you can crystallize your compound, racemic mixture. You can crystallize the racemic mixture. Okay, crystallize the compound, racemic mixture slowly. Okay, by you from a suitable solvent, it's all very tedious job. From a suitable solvent and observe the crystals. Observe the crystals. You can see that if the crystals See here, it is not directly that you observe the crystal. It's better that you observe the crystal by through a microscope. It is not possible to identify the crystal in nature by your naked eye. So you have to observe this through a microscope. If the crystals are distinguishable into distinguishable into right and left. Distinguishable into right and left handed, just like a pair of gloves. They can be picked, separated. They can be separated, separately picked up. So this is really the mechanical separation. This is what is mechanical separation. Now you have a lot of disadvantage for this. What is that? First thing, you should get the right solvent. The right solvent is very difficult to get. Okay. And second requirement is the crystal should be mirror images of each other. It need not be that all of them, all the molecules will crystallize into mirror images. There is no rule like that. You have to make a study, and crystallization should be into mirror images. Crystallization should result in crystallization should result in mirror image crystals. Mirror image crystals. Remember, this is very difficult. Okay, once you get the solvent and then you start crystallizing, still getting a mirror image crystals are very, very difficult. So rarely it happens. A very typical example which we know is sodium ammonium tartrate. Sodium ammonium. Sodium ammonium tartrate is a compound. And see, the first person who invented this optical activity, the first person who invented optical activity is Louis Pasteur. You must be knowing Louis Pasteur, but for many reasons, he is the first person who found out optical activity in organic compounds. And the first compound was sodium ammonium tartrate. So what this is how accidental. He had prepared, he had tried to crystallize this compound, and he had kept this in a beaker and added water and just labeled it what it is. After about 2 months vacation, he came back to the lab and found that it is all got dried up. The water has got totally evaporated, and he saw a lot of crystals down on the inside the beaker. So he was very curious, and what did he do is he took the sample of these crystals and observed under a microscope, and he found that they are mirror images of each other. They are mirror images of each other. And therefore, what he did is he took a forceps and he started separating the mirror images by just like, as I mentioned earlier, the pair of chappals or pair of gloves. So he separated them into A and B. In one vessel, he put A, and the other vessel he separated. He put B. And the equal amount of these two he has taken and checked, prepared solutions and checked optical activity. He found that they are having equal rotation in opposite side. If this is right side, this is left side. So this is the first invention of optical activity, and you should be quite lucky to get these results. And this method cannot be practically used in large scale. Okay, now, so that is it is not having much of a significance. A second method is a biochemical method. Number two, biochemical method. This is quite interesting. The moment something which you will be of interest, having some interest, biochemical. The great idea is you should have some microbe. You should have some microorganism which will destroy. Oh, not able to write it on the board. Which will destroy one of the enantiomer, leaving behind the second one, which will destruct one enantiomer. Okay, so you should have a right microbe. Okay, and now one will be eaten by this microbe, the other will be left behind, and then you can take that solution and crystallize it. Crystallize the second one. Second one. Now this method is also having a lot of disadvantage. Now here there is an example is DL tartaric acid. DL tartaric acid. You take DL tartaric acid and put some mold penicillium glaucum. Add penicillium glaucum into this. What penicillium glaucum is doing is, it will destroy the D. It destroys the D isomer. And L will be left behind. So L is separated. And you understand one thing, there is a great disadvantage for this method. You are sacrificing 50% of the material. Okay, so that is one of the problems that you will face. Disadvantage is 50% of the material is 50% of this material is lost. Secondly, getting the right microorganism is very, very difficult. Getting the right microbe. That is very difficult. And third way, the third disadvantage is there are certain enantiomers which are poisons to microorganisms. Microorganisms should not get destroyed inside. Okay. So this is the second method, biochemical method. This is also not practical in the large scale. In the large scale, it is not practical. Not practical. Now the third method is the most important method, which is known as chemical method. Chemical method of separation. So mechanical method, biochemical method, and now you have chemical method. Now there is a basic principle behind this, which you should learn. That is, we have seen that the enantiomers, they don't have any difference in the physical and chemical properties except two. One is optical activity and the other is chemical reactivity towards chiral compounds. Chemical reactivity towards chiral compounds, that is one, and the second one is optical activity. There is no other difference between the two. They have the same solubility, they have same melting point, they have same boiling point. So that is the disadvantage of separating them. But you can take advantage of another fact. The second fact is diastereomers will differ in their physical and chemical properties. So you take advantage of this fact. What do? You take your racemic mixture, take the racemic mixture, take the racemic mixture, okay, which contains two enantiomers, react with an optically active compound. Optically, optically active compound. React with an optically active compound. Okay. One optically active compound, you have to, one is plus and the minus. It's a mixture. Now what will happen is, since you are reacting with an optically active compound, you will get two compounds. A mixture of two compounds will be formed. Okay. I think the connection is gone.